Now, in general, a perception is that the gravity is something that belongs to Earth only. Gravitational force. If somebody asks you what is gravitational force, the most of the time, the people say that the force of Earth on us is the gravitational force. That is not true. Gravity belongs to every mass. Newton discovered that every mass in universe attracts every mass this force of attraction is gravity. This force of attraction, gravity. We go into Newton's law of gravitation. Newton has mathematized this force. So here every mass attracts every other mass. This force of attraction is directly proportional to product of. So force of attraction does not depend on one's on both masses, actually the product of the masses. Gravitational force is directly proportional to product of masses and inversely proportional to square of between their centers. Okay, so Newton says that every mass in universe attracts every other mass, and uh, like some of the very important formulas in physics, some very important phenomena in physics that you can apply categorically everywhere without any condition. Gravity is one of it. Has no condition. Like uh, in it will be applicable in all situations in the universe, whether it is one proton next to another proton or it is one galaxy next to another galaxy. There will be force of attraction between them. From very micro to very macro, the force is always there. This law applies everywhere. So that's why it's very important. Well, Newton has given us some of the laws like that. For example, Newton's third law: every action has an equal and opposite reaction. This law has no condition, no no limitation. Like it will be applied to every case, everywhere in the universe. Similarly, law of gravity: every mass attracts every other mass, and this is a categoric statement. There's no condition, there's no uh, case where there will be no gravity or less gravity, or gravity will not act on another thing. Okay, so if we have two masses, now I'm making a diagram and converting the same statement into a mathematical statement. This is mass number one, this is mass number two, and I'm making them like a point so that the distance between them is far more than their size. So their size becomes irrelevant. This distance is, because this is a radial distance, so we take it in terms of r. According to Newton, force of gravity is directly proportional to product of masses m1 multiplied by m2. Force is inversely proportional to square of distance between the centers. So that means force is directly proportional to m1 into m2 over r square. Now, this means if force is directly proportional to m1 m2 over r square, then force divided by m1 m2 over r square should always be a constant. So that constant was found later, and it was capital G m1 m2 over r square, where G is universal gravitational constant. And why do we call it universal? Because it will apply anywhere in the whole universe. And the value of G is 6.67 into 10 to the power minus 11 Newton meter square for each kg square or per kg square. So this is the value of G. It is also given in data, but I think you will be using it so many times that you will automatically remember it. So the formula for force between them is F equals to G m1 m2 over r square. So there will always be gravitational force between any two objects. But why don't we observe, or why don't we feel the gravitational force between one person and another person? Or why don't we feel gravitational force when we are standing near a huge building? There should be a gravitational force between me and a mountain and a large building. And there is. But the problem, why don't we feel that gravitational force? Answer is because of a very strong gravitational field nearby. For example, if and this diagram is not to scale, so don't think that I'm putting two giants over here. These are two people, and they're standing on Earth. So the problem is that there is a very strong gravitational force on them that does not allow us to feel gravitational force between them. Let's say two people are standing approximately 1 meter apart. This person has mass 80 kg. This person is 60 kg, and they are standing 1 meter apart. Let's calculate how much gravitational force is acting on them if they are standing 1 meter apart, center to center. Let's see. F equals to G M1 M2 over. So G is 6.67 to 10 to the power minus 11. M1 is 60. M2 is 80 divided by 1 square.
3.2 times 10 to the minus 7.
3.2 into 10 to the power
Minus 7.
7 Newton. So that is like 0.00000032 Newton. And there is a force of gravity on this one is approximately 600 newtons and 800 newtons. Do you think forces 100 and 600 newtons acting on you, you will be feeling a force of 0.00000032 newtons? Like, will that force be noticeable?
No, sir.
No. That is why we do not notice these small forces acting on us, but they are acting. So this is how we can find out gravitational force between any two mass. Okay, if we have started to talk about Earth, let's keep talking about Earth. If this is Earth, and I put you over here. Actually, I don't understand why every person himself on the top of Earth. I always consider myself somewhere here on Earth or here. Okay, so we can be any one of these three people. But let's say the mass of Earth, let's call it capital M. This is a center of Earth, core of Earth. This will be the radius of Earth. The distance of the person from the center of Earth will be radius of Earth, and the person's mass is M. Information is that the radius of Earth is 6.4 into 10 to the power 6 meters. Now, force of gravity between person and Earth equals to G M M over R square. Does this make sense?
Yes, sir.
If the person is R distance away from the center of Earth, and I uh, person's center will not make it. The person is very, very small as compared to the radius of Earth. So his height will not make any difference. Now, what will be the weight of the person? Do you think it will be mg?
Yes.
Near the surface of Earth, gravitational force of Earth is called weight. Do you agree with me on this? The gravitational force of Earth is called weight.
Yes.
Do you think GMM over R square equal to mg? And I can cancel m and m. I can make m the subject of formula. It should be GR square capital G. Value of R is 6.4 into 10 to the power 6. Seven into 10 to the power minus 11 Newton meter square for each kg square, and G is well known, 9.8 newtons per kg. So who can find me the mass of Earth? Find me the mass of Earth? Anyone?
Six 6.02 times 10 to the
Anyone get it?
24. Hello,
Okay,
sir.
let me confirm it with someone else. Anyone else?
I got the same.
So when we put 9.8 into 6.4 into 10 to the power 6 whole square divided by 6.67 into 10 to the power minus 11. What did you get?
Uh, 6.02 times 10 to the 24.
6.0 into 10 to the power 24 kg. So that is the mass of Earth. How simple it is to find mass of just sitting home and using a calculator. Now, who can find me the density of Earth? Average density, I should say.
I'm not sure, sir, but 5486.
Sorry, 5, 4.
86.
Maybe another person can. So I have made a formula for you because density is mass over volume, mass divided by 4 by 3 pi r cube. It will be 3 times m, because you know that when we are dividing a fraction, we can flip the fraction and change the sign from division to multiplication. So it will become 3m over 4 pi r cube. So values in power 24 divided by 4 and pi and r cube 6.0, sorry, 6.4 again. Into 10 to the power 6. So what do we get? Everyone in the class should do the calculations in your calculator, because you should be getting used to with the calculator.
1.7 into 10 to the power 22.
1.7 into 10 to the power
22.
22. No. Actually, one more thing that student do in calculus, which is not
Oh, so
good,
I
is,
forgot to gratify it.
sorry, what did you do?
It's 5.4 into 10 to the power 21.
5.4 into 10 to the power
21.
11,
21.
21.
So I got
No,
5464.
actually, okay. You got 3. She's getting 21. Actually, the fight is about the power here. Now, when you're putting values in calculator, now they do is they press 6, then point, then 0, then multiply, then they type in 10, and then they use the calculator way of putting power 24. Instead, this is how you should not do it. You should do it like 6.0, and there will be a button that has exp on it, which is a short of exponent, and then 24. On calculators, it will look like 6.0 E24. And this is how it should be. Because you know why? Because when you will be putting 6.4 into 10 to the power 6 cube. Now, what happens is student does 6.4 into 10 to power 6 cube. And calculator only cubes this thing and totally ignores this one. Instead, if you do 6.4 exponent 6 cube, then calculator understands that this is one value. So he cubes the whole thing. This is a calculator tip. Use this and calculate again. I hope you can see the EXP button over there.
Yes, sir.
Okay. So do not use that multiply sign and then 10 and then power, because there's always a chance of making a mistake over there. And plus you have to press so many buttons. When you press EXP, all you have to do is just put the positive or negative number, whatever the power is, and calculator will understand that this is one single value. If you square it or cube it or under root it, calculator will understand what to do.
Yes, okay, sir.
Okay. Are you getting the same value? So your answer is 5478.
I got 5464.
5464. Let's see. What is your answer?
5464.
So it will be 5.5 into 10 to power 3 kilograms per meter cube. So this is the average density of Earth. Now, uh, gravitational field strength. What is gravitational field strength? Gravitational force per unit mass at a point is gravitational field strength at the point. Okay. Now, gravitational force per unit mass at a point is at a point in a field is gravitational field strength at the point. So gravitational field strength equals to gravitational force divided by mass. Gravitational field strength is represented with small g, g and m over r square divided by m. And I hope you can see m and m got cancelled. So g equals to gm over r square. Unit of gravitational field strength is newtons per kg. Near the surface of a planet or any large gravitational field strength is equally equal to gravitational acceleration. Gravitational field strength is gravitational force divided by mass. But near the surface, weight equals to gravitational force. So this is a very common question examiner asks again and again, that why gravitational acceleration and gravitational field strength have same value. You can say that the gravitational acceleration is called by the weight of the object. If weight is acting as the net force, so F equals to ma states that gravitational acceleration has to be weight divided by mass. Gravitational field strength is gravitational force divided by mass. And near the surface, weight is equal to gravitational force. That's why we are actually dividing same force with same mass. So you're supposed to get the same numeric answer. Although gravitational acceleration is in meter per second square and gravitational field strength is in newtons per kg, but they have same numeric value. For example, near Earth, gravitational acceleration is 9.8 meter per second square. Gravitational field strength is 9.8 newtons per kg. On Mars, surface of Mars, gravitational acceleration is 3.92 and gravitational field strength is 3.92 newtons per kg. Gravitational acceleration is 3.92 meter per second square. On Moon, gravitational acceleration on the surface of Moon, gravitational acceleration is 1.6 meter per second square. And gravitational field strength will be 1.6 newtons per kg. Okay, tomorrow we'll be sketching some graphs for gravitational force and gravitational field strength. This is it for today. Any questions?